Welcome everyone to my channel. So question number 11, degree of kinematic indeterminacy of the beam shown in the figure 12.2 is. So we have to determine the degree of kinematic indeterminacy of this beam. Okay. So we know the formula, degree of kinematic indeterminacy dk for this rigid jointed plane frame equal to 3j minus m plus r plus summation of r dash. R dash is the additional number of equations required due to hybrid joints, we know, and this R dash is required when the frame is involved with internal hinges. Okay, and R dash equal to n minus 1. So for these hinges, R1 dash will be equal to n minus 1. N is the number of span connected for the hinges, so two number of members connected for this hinge, so 2 minus 1 equal to 1, so R1 dash equal to 1. And for these hinges, two members are connected for these hinges, so R2 dash will be equal to n minus 1, that means two number of members, 2 minus 1 equal to 1, so R1 dash equal to 1, R2 dash equal to 1. Okay, and number of joints will be equal to 1 2 3 4 5 6, and number of members will be 1 2 3 4 5, and number of reaction components will be one horizontal and one vertical reaction from these hinges, and one vertical reaction from this roller support, and one vertical reaction from this roller support, and one vertical reaction from this roller support. So total 5 numbers of reaction components available from this structure. So by putting all the value into this equation, we will get degree of kinematic indeterminacy dk equal to 10. Option D is right answer. Question number 12, the rigid jointed frame shown in the figure 12.3 is. So this is the rigid jointed plane frame. Okay, we have to find out the degree of static indeterminacy of this frame, and a formula we know 3m plus r minus 3j. M is the number of member 1 2, m equal to 2, a number of joints equal to 1 2 and 3, a number of reaction components will be 3 because two reaction we will get from this support and one reaction from this support. Okay, this is in support, that means one vertical reaction and one horizontal reaction we will get, and this is roller support, that means one vertical reaction we will get only. So r equal to 3. By putting all the value into this equation, we will get ds equal to 0. So we know if the degree of static indeterminacy of a structure is 0, then the structure is stable and statically determinate. But if the value of ds is less than 0, the structure will be unstable. Okay, but if the value of ds of any structure is greater than 0, then the structure will be stable and statically indeterminate. Stable and statically determinate, option B is right answer. Question number 13, the degree of kinematic indeterminacy of the pin jointed frame shown in the figure 12.4 is. This is the figure. So this is a pin jointed plane frame, and we have to calculate the degree of kinematic indeterminacy of this frame. Okay, we know the formula dk equal to 2j minus r. J is the number of joints will be 1 2 and 3, j equal to 3, and reaction components will be 4 because for these hinges supports one vertical reaction and one horizontal reaction we will get, and from this hinge support we will get one horizontal reaction and one vertical reaction. No moment will be there from these two support. Okay, so r will be equal to 4. So by putting j equal to 3 and r equal to 4 in this equation, we will get dk equal to 2. Option C is right answer. Question number 14, the number of independent equations to be satisfied for static equilibrium in a phase structure is 6, and the 6th equation will be summation of all the forces in x direction equal to 0, summation of all the forces in y direction is equal to 0, and summation of all the forces in z direction is equal to 0, and the moment at xy plane is 0 and summation of all the moments in yz plane is equal to 0 and summation of all the moments in zx plane is equal to 0. So total 6 number of independent equation available for space structure. Option D is right answer. Question number 15. The degree of static indeterminacy of a pin jointed space frame is given by m plus r minus 3j. Option B is right answer, where m is the number of unknown member forces, r is the unknown reaction components, and j is the number of joints. Question number 16. The degree of static indeterminacy of a rigid jointed space frame is 6m plus r minus 6j, where m, r, and j have their usual meanings as stated earlier. Option D is right answer. Question number 17. The degree of kinematic indeterminacy of a pin jointed space frame is 3j minus r. Option B is right answer, where j is the number of joints and r is the reaction components. Question number 18. The number of independent displacement components at each joints of a rigid jointed space frame is 6. Option D is right answer, because I discussed earlier forces in x direction, forces in y direction, and forces in z direction, and moment in xy plane, moment in yz plane, and moment in zx plane. So total 6 numbers of independent displacement components at each joint of a rigid jointed space frame. Option D is right answer. Question number 19. If in a rigid jointed space frame 6m plus r is less than 6j, then the frame is. So from the question we have got 6m plus r less than 6j. So we can also write 6m plus r minus 6j is less than 0. Okay, so we know 6m plus r minus 6j is the degree of static indeterminacy of a space frame or space structure. So if we know, if the degree of static indeterminacy of any structure is less than 0, then the structure is unstable. So the following frame will be unstable. Option A is right answer. Question number 20. The principle of virtual work can be applied to elastic system by considering the virtual work of internal as well as external forces. Option C is right answer. The principle of virtual work states that if any particle or system is in equilibrium by the action of all internal as well as external forces, then the virtual work done by all the forces acting on the system is 0. Suppose this is a body pushed by external force F. When the body is pushed by the external force F, then the internal reaction will come up from the body to counteract these external forces. That is internal force equal to R. Okay, so for the particle in equilibrium or body in equilibrium, internal forces will be equal to external force. Okay, so R will be equal to F, and the system or body is in equilibrium. Okay, in this case the virtual work done by the internal and external forces is 0 for this system.